Today, let's talk about what it takes to claim statistically reliable inferences. What does it mean? Let's talk about hypothesis testing. So when we collect the data observations and extract their characteristics, let's say averages like average house prices across neighborhoods, we may notice a pattern, like average price in one area somewhat higher than the other. But sometimes it might be just a matter of data noise. For example, you saw only a handful of houses sold in one area, and one of them accidentally turned out to be a super expensive estate, strongly pushing your average up for such a small sample you have. So maybe just an outlier, which is not representative to the entire neighborhood. Or maybe it's actually part of the pattern. So what would it take to claim the pattern you observed at a statistically significant level? So now let's zoom into the quantitative approaches we can use for that and start with an example of children gender analysis. Start with a small sample and imagine for the 3 observed cases, we got all 3 girls. Is it enough to claim a pattern? Can we claim the probability of girls being born is 100%? Or is the sample too small for that? A good way to understand it is to assess the odds of observing such an outcome just by chance, under normal conditions. We just need to specify what normal conditions are. We'll later call it null hypothesis. In our case, use normal belief that genders are equally probable. So now if we find that the observed outcome can perfectly happen by pure chance under those normal conditions of equal probabilities, we shouldn't take it as an evidence of the contrary. Under those normal conditions, the chance of observing 3 girls would be 1/8, 1/2 power 3, or 12.5%. Somewhat low, that's true, but really hard to claim it as barely possible. So this observation alone might not really be enough to reject the assumption that the probability of a girl is 1/2. So while this observation might make us suspect the possible pattern, by itself, those 3 observations won't be enough to convince us that there's indeed a pattern. Let's say now we have the data on 100 children, and 55 of them are girls and 45 are boys. Would that qualify as a pattern? Can we claim the probability of having a girl is 55% based on the sample that big? Again, assume equal probability for boys and girls and call it a null hypothesis H0. This will serve as a probabilistic baseline for assessing the results of our observations. Under those conditions, the probabilities of each outcome for the number of girls within 100 observations are described by a binomial distribution, defined by the following formula where expression marks denote factorials. The height of the bar on the plot represents the odds of observing a given number of girls. For 55, we can see it around 5%, but due to a large number of possible outcomes, the probabilities of each specific value, even the most probable ones, like 50, are all below 8%. What we'd rather consider is a cumulative probability of all the outcomes at least as extreme as 55 girls. So if you order all the outcomes by their likelihood, where the 55 girls actually are in this sequence. Such extreme outcomes include, first of all the cases of having at least 55 girls, as having more comes with a lower probability. And using the cumulative distribution function for binomial distribution, we can find those having a cumulative probability of 18.4%. But given that the distribution is symmetric, other equally extreme outcomes are having at least 55 boys, or less than 46 girls. And those again total at another 18.4%. So the total probability of all the extreme outcomes is 36.8%. This means that the event of having 55 girls lays within 37% of the most improbable cases. But it's also located within 73% of the most probable cases if we look at the cumulative probabilities of the outcomes between 45 and 55, including those. So nothing really looks too improbable about this event of 55 girls. And this way we can't reject the null hypothesis. We can't exclude that the observed event happened under those baseline conditions just by pure chance. And there is still no reason to reject the assumption that genders are in fact equally probable despite this specific observation. Now what about a larger sample of 1000 children, out of which we're going to see the same proportion of 550 girls and 450 boys. This time, assuming an equal probability of boys and girls as a null hypothesis, we can find the cumulative probability of at least 550 girls as low as 0.087%. The same for having at least 550 boys. And the total for all the outcomes at least as extreme as 550 girls would be only 0.173%. So the event falls within 0.2% of the most improbable cases, which means that we can now reject the null hypothesis with 99.8% confidence. And by rejecting the null hypothesis, we'll move to an alternative assumption of having uneven odds for the genders at birth, which we are now 99.8% confident about. Important to mention that despite low probabilities, there is still a chance that the observation happened at random under the baseline conditions of the null hypothesis. In the probabilistic world of uncertainty, we can never reject the hypothesis for certain. So we have to select the target degree of confidence at which we reject the hypothesis that turned unlikely. This level is usually set up at 95%. If the hypothesis is less than 5% likely, we reject. But in some high-stakes situations with lower error tolerance, we may have to increase it. Also important to note is that we didn't prove the specific probability of 55% for a girl. We're only rejecting the even odds. If we need more than that, we can also evaluate possible intervals for the probability and find the interval to which it belongs to with, say, 95% of confidence. But this is already a subject for inferring probabilistic models. We'll talk more about that when considering Bayesian inference.